So we're going to talk today about frameworks, maps, tools, patterns, things that can assist you if you actually go forward and do risk-based decision making. But first, I just want to, let's go back to the old days, you know, and it was so easy because we just went around to places and we saw these beautiful things and we said, oh, that's what we got to do. It's just that, right? It's best practice. That's what we need. We get that. We got it. We're caring for our collection properly. Oh yeah, well, getting the money might have been a problem from time to time, but it was so clear because it was visual, right? That's what we were aiming for. Now these guys, they want to make risk-based decisions. Adopt a method. Yeah, I want that, right? You want that? They want you to do numbers and graphs. Oh. But you just did some risk analysis. Did you watch yourself do that? You see, you've already done it. And it's really interesting. And you'll never think about preventive conservation the same way again once you start going into this method. And it really, you know a lot already. It's not that difficult. It's just a different way of thinking about things. So what I'm going to do in this talk is just start to give an overview of some of the tools and the frameworks and the ideas that are out there that can help you get to understand how to do this kind of thinking. And the first one's easy because you already know it. Probably. It's the 10 agents of deterioration. So I'm going to start with some frameworks. These are things we use, and Rob referred to this earlier today. These are structures that we use to think systematically about things. And the agents are just one way that we can use to look at a problem and then say, what's really going on here? And you kind of use the agents when you were looking at the totem pole risks, because you say, what kinds of things could harm those totem poles if we put a big party in the middle of the room? It's particularly important when you're doing comprehensive risk assessments because you want to make sure you cover the whole range of possible things that could go wrong. But it's also really useful in a focused decision-making situation where, again, you want to tease out what are the parts of the problem and how does the damage actually occur. It's not enough to say damage happens. You have to, as you saw with those risk summary sentences, you have to figure out what the agent is and then how it creates damage. And the agents are part of the framework for preservation that CCI puts out, so you probably know it from that. In that framework, you also have the 5 stages of control. So again, these help us think about how much damage is likely to occur in a certain situation, because we look at, are there things in place that help us avoid that agent or block that agent from getting to our collections? Or do we have things that help us detect the presence of an agent so that then we can respond, perhaps more quickly than otherwise, and prevent something from happening or prevent it from getting too bad, really bad damage? Or there's always, in the final fallback is, well, nothing else worked, but we respond and we keep the damage, we treat the damage or at least learn from that experience, and next time it won't happen. And each of these stages of control we can apply at 6 different layers. So we're starting right at the object in its mount or its storage container. Or we can look at fittings that support the object, display cases and storage furniture, for example. All of those things might be in a room. So some of these various things that are protecting your object might be at the room level, or in the building that houses the room with collections, or on the site around the building in which collections are housed. Or we have to push it right back even to the region, because sometimes the risks are associated with that building being located in a particular geographic location. So again, by sitting down with these 6 layers, we can think very systematically about how risks occur to a particular collection. So these are simple. These are just thinking tools, but they're really basic at that first stage when you're trying to figure out risk summary sentences. These are extremely helpful. Fortunately, we can go past that, and we already have some models around certain risks to help us start to put numbers on things. And I'm going to talk about a few of those. And the first one I'm going to talk about is what we call a control level. And what is a control level? In general, a control level is a series of protective measures that are grouped according to certain levels of protection that they give to a collection. And they're often organized by the stages of control. So you see at the top of this chart, the control level is 1 to 6 down the left side, and then at the top, these measures are grouped by void, block, detect, respond, recover, often that way, and sometimes there's a few extra different kinds of columns as well. But they're grouped in a sort of a meaningful manner, and then as you, the least control is number 1, and as you go down the list towards number 6, you have increasingly sophisticated control over that particular problem. So you have less possibility of damage to your collection. How do you determine your control level? You simply go through the measures and you check off which ones you have and which ones you don't. And as soon as you have those all checked off, it's usually in a control level system the highest number in which you've checked off everything that gives you your control level. So that's usually how it's defined, something like that. So in this case, this person, oh, one of my little check marks kind of flew up on the top there. I'm not sure what happened. Anyways, number 1, it's all there, but number 2, there's significant gaps. So this institution for our problem, which we haven't defined yet, would be at control level 1. But what does that mean? Let's put it in terms of specific agents of deterioration. CCI scientist Jean Tétrault has developed a control level approach to fire, and we've talked about that earlier. And there's the citation for the paper in the Journal of the Canadian Association for Conservation of Cultural Property, and it's available to everybody on the web. In his paper, he shows how the control levels are associated with a likely frequency for fire. So if your institution worked out this chart and said, oh, we're at control level 1, then it's very probable that you will see a fire of some size approximately every 140 years. And it can go up to, based on this model, if you have all the protection measures in place, a control level 6, the estimate working with a fire expert is that it's going to be on the order of 2,800 years that you have a fire of any size. So you can get very, very good control and really reduce the chance of having any kind of fire. But most of the people that we are working with, we're finding, are more in the control level 1 to 3 range. The other control level that we have available here that has been produced through people from CCI is for pests, and this is work from Tom Strang and Rika Kagawa that they've developed for pest risks, and it's in CCI Technical Bulletin number 29, which is also available on the CCI website, and works a similar way. You just look at the various measures in place and see which matches your institution. For things like fire that occur infrequently, we need some kind of tool to help us establish the A-score, the frequency, because it's not within our own experience. They happen less frequently than most people's careers, unless you're in a really fire-prone area. And it's the same for a lot of natural hazard risks. You need help. You need statistical help to understand the A-score for these kind of risks. But fortunately for natural hazard risks, it's not just heritage institutions that are affected. There's a lot of people, a lot of areas, different cities, and everybody being affected by these kinds of issues, and therefore lots of people are interested in the frequency. And for that reason, we have access to natural hazard maps. So I'll give you a couple examples. Big one, of course, is earthquakes. The map of Canada showing the various earthquake zones in Canada. The zones depicted here are linked to the damage expected for an earthquake that has a probability of 10% in 50 years, or what we can call a return period of roughly 500 years. And this data is out there. It's described in terms of that frequency, so we can use that to analyze the risk of that very big earthquake. But to complete the whole risk, we have to understand the damage. And to do that, you figure out your zone, and then that gets linked to what's called the modified Mercalli scale, which categorizes the intensity of earthquakes in terms of observed damage. So I've just given you the definitions for the red zones, which are the areas in Canada that can expect the absolute biggest earthquakes. And in those higher zones, they tend to be described in terms of what's going to happen to buildings, so what kind of buildings you can expect to collapse. They don't necessarily give much detail as to what's going to happen inside the buildings, but I'm sure you can imagine that if your building collapses on top of your collection, you have a problem. You also have a problem, however, if all you've done is reinforced your building and you haven't done anything to secure the collections inside those buildings. But it gives you an idea, and we can use this information to do an analysis. Flood hazard maps are the other area where we can get really good information to understand risks. I'm showing you the best, and this is becoming increasingly available over the internet. The best material in Canada is available for Alberta, because they have a nice mapping application for the whole province. And here I'm showing you downtown Calgary, since they had very big flood issues just a few years ago. Just to explain what's going on, the red areas are what is called the floodplain. So this is the area that, and all of these areas that are sort of pink or red, it's modeled as the area that has a 1% risk of flooding in any particular year, or it's about, it's a return period of 100 years. Is that a 100-year flood? The red areas are where the water is going to really move very fast. And so that's the floodplain. The flood fringe, the waters are probably moving less quickly, so there's less damage just from the force of the water per se, but quite frankly, if it fills your storage basement, you don't care. It's still water damage. And the overflow areas, again, it's part of the flood fringe, perhaps, these are all part of this 100-year model floods. So if you're in these areas, if you're in Calgary and you want to place a museum, where are you going to put it? In the yellow area, I hope. That's the Glenbow Museum. They were smart. National Music Center, on the other hand, what I'm showing you is their current location and the new location, where they're building their new building. Okay, what were they thinking? I guess the fortunate part of the story is that as they were excavating the new site, the 2013 floods happened, and the excavated site filled up with water. They were going to put their storage in the basement, which is where part of their storage, but not their most important part of their collection, was in their current building. So it was like this. It's like they just lost part of their collection. They're not putting their storage in the basement of the new building. End of story. It's decided. I'd like to see a lot more use of these kind of maps to prevent the building of the even thinking about putting storage in a basement on a floodplain. And geospatial maps like this are becoming more and more apparent for various kinds of risks available because the technology's there with GPS and things that we can do things. And Tom Strang at CCI is currently working on building multi-hazard maps for risks associated with Canadian museums, and I'm looking forward to seeing the kinds of things he's coming up with. So those are kind of like those big risks, and we can get a sense of how frequently or whether they're going to occur to our institution. But what about those things that we love so much, which is the things that happen more gradually, like environmental problems and light problems, you know, the stuff we always worried about forever? Well, we have tools for those as well, so you can do those ones too. And I'm going to start with color fading. Here's a picture. Actually, it looks better on my screen here, but it shows it. 2 chairs from Eldon House when we did our risk assessment, and you can kind of see the one on the right, it's looking a little bit duller than the one on the left. So it's the same fabric, it's sort of part of a set. We've taken the cushions off the front of that one so you can show what the original color was like. I'm going to use these 2 chairs to just do a demonstration of how you can use CCI light damage calculator and the associated data that's behind that calculator to start analyzing a light risk. So here are 2 chairs, and I've pulled a suite of colors from the light damage calculator that is the collection of textile items in the light damage calculator. And when you choose one of these collections, what you have here is on this end you have the very sensitive dyes, and on this end you have the less sensitive dyes. So this is a range from very sensitive to barely sensitive at all, okay? So, and in between, in the middle. Because textile, you don't know how sensitive the dyes are, so we assume there's a mix. These chairs are in a Historic House Museum collection. Actually, they were in the Historic House before it was a museum. And so let's just say for 50 years, they were in the house, just doing what chairs do, in front of windows, whatever. And then it became a museum, and another 50 years, they just sat in the same place again because it's a historic house museum, so you just keep it looking like what it was when it was a house, right? That's the idea. So it's 100 years in the light in a historic house museum. The windows have no UV film because it's just a house. And it's actually a pretty dim house. If you just go around on an average day and you take light readings, it's about 50 lux. They had to install actual electric lights just so people could see the museum when they went through. Otherwise, the volunteers had to take flashlights to let people see what was on display. So it's not very bright. But it's 100 years under those conditions, and we can say approximately it's, on average, about 12 hours of light a day at that level. And the chair on the right was sitting near the window. So here, what I'm showing you is what you would enter into the light damage calculator to model that situation. Now I'm going to show you the result. So this is when they were made. Now this is 100 years later. And you can see, it sort of looks like our two chairs. Okay? And you can see, if you look at the very bottom, the light damage calculator estimates the megalux hours of exposure under those conditions. So the one had a lot of exposure. The other one was in a corner. The fabrics were covered up. They had to clean it once in a while, but hardly any exposure. So the colors are almost as they were originally. A little bit of fading here on the sensitive one. But the one that was in front of the window is looking like this. Okay. This has already happened. Too late. Can't do anything about it. Dye fading. So what you're really now interested in, if you're going to model the risk, is the future. You're starting with this. Now you say, okay, let's put some UV film on the windows. Let's deal with this problem a little bit. UV film goes on the windows. And then somebody says, hey, let's pull that beautiful chair from the corner out closer to where people can see it in front of the window, because then people can see the original colors of this fabric. And this new display is going to stay up for 30 years. Let's model the next 30 years. So we're going to put it in the light damage calculator. And in this case now, we're going to assume both chairs, the fabrics of both chairs, are exposed equally to the same conditions. So that's what we're showing in here. So, but they started from a smaller exposure, but they're getting the identical additional exposure. See here at the bottom? So what happens? The light damage calculator can show you. Well, both are faded a little bit more. But in terms of risk, the loss of value for this chair is not necessarily the same as the loss of value for this chair. This chair, well, you may not even see the difference because it already looked pretty faded. But this chair looked pristine, and now it's starting to look a little bit dull. So here's where, when you're analyzing this risk, you can say, in 30 years, there's this amount of loss of value, but you see how the loss of value depends on where the chair started in the first place. Of course, if you have some time and money, you can do some microfake testing and test every single color in the textile, or in this case, it's a piece of work on paper, and find out exactly how sensitive the colors are and whether, therefore, how fast they're going to fade. In this case, 90% of the colors in this particular example were highly sensitive to light fading. And then you can make decisions that way, too. So let's go to our most favorite topic when we're thinking about collections, which is relative humidity and temperature. Those crazy storage places that have absolutely no environmental control. Because we have some tools that can help understand this kind of risk as well. This is a very typical graph that you will see in a space that has very little control. It gets very dry. Actually, this has a bit of humidification in the winter. This place with no control would probably drop down closer to 0, depending on your climate. Obviously, it has heating. But you can also see they're letting the temperature drop a little bit in winter. This is a warehouse space, but the humidity goes very high in the summer, drops very low in the winter, and you see lots of crazy peaks all the way around. So you may be surprised when I tell you that if we look at a material like acidic, very acidic paper, which I'm going to call this very acidic paper, or unstable material like rubber. It's not really the relative humidity that's your problem, it's the temperature. How can I say that? In fact, I'm going to say that storage in that room that gave the graph that you just saw is actually no worse than putting it in our beautiful climate-controlled 50 plus or minus 5, 20 plus or minus 2 degrees Celsius storage room. How can I say that? Well, because we have a tool. There we are. We have equations that model the decay of materials like paper, the Arrhenius equation, and they predict the course of thermal aging or chemical decay. This has been scientifically established. And we can use those equations, Stefan Michalski can use these equations, to create what we call a lifetime calculator, which is essentially a spreadsheet where we put some average environmental data in it, of a particular space, and it will tell us how long a piece has before it reaches what we call the end of its lifetime. So here you see on this graph, we're thinking about a material that has a relatively low chemical stability, a material like newsprint, okay? Generally the class is 30 to 100 years, but newsprint, 100 years in a museum type setting, normal room temperature, is probably pretty good. So this is in what we call ASHRAE class AA storage environment. The best anybody ever does, okay? So it's going to last about 100 years, all right? So now I'm going to show you the graph. This is the graph where it's warmer in the summer, a little bit cooler in the winter. You see here, warmer, this is summer, this is winter. It's humid in the summer, it's dry in the winter, and the fluctuations are like plus or minus 10 on average. And actually, you know what? That stuff's going to last about 143 years. Why? Because the chemical decay processes go faster in higher temperature, and this is cooler in the winter. It's also a little bit drier in the winter, which also slows those processes down a little bit. So we put those numbers in the calculator, and it tells us approximately how long it will take before it gets to the same amount of deterioration as that blue line. What's really nice about this calculator is to test out numbers to say what can we gain if we really change the environment. So let's say the decision was, what if we cool down that space? Let's not talk about building a new space. Let's just cool down that space so that it's 16 degrees Celsius year-round. Well, if we do that, we probably have to expect a little bit of pushing up of the relative humidity in summer. And it's not necessarily going to it's going to be the same in winter, right? But when we do that, we can see just keeping it cool all year round is going to double the life of the newsprint. So this is a really useful tool for just helping us understand how both relative humidity and temperature, but it's mostly temperature driven, affects the progress of the decay of various materials. It's not just these low chemical stability materials, because you can set it up to look at medium chemical stability materials as well. We usually don't worry too much about things that are pretty stable under these conditions, because they're going to last long enough anyways. But it's these low chemical stability ones that we worry about. So a very useful tool that's gradually becoming available for people to use. We've just been using it for a couple of years at CCI. So now we get to the pattern part of the talk. And this has already come up. Yes, there can be tools, and you have to sit and figure out the risks, but a way to get closer to understanding what your risks might be to see what's happening in institutions that have well-analyzed risks. So what I'm going to talk about a little bit is what we've seen in our projects. But just as a guide to understanding what you see in other risks, no two institutions are identical, so you have to be careful at how you look at it. But what we can do is kind of say what risks get slotted in these categories of risks that you see in the chart. And this is from the manual. Based on magnitude of risk score, they're related to a category in terms of priority, and we illustrate these by using traffic light colors. So the redder the color, the higher the risk, the bigger potential problem to your collection. The bluer the color, the lower the risk, maybe it's being well managed. And so we can start to see some patterns in terms of what kinds of risks fall into those categories. So for example, we did 2 historic house museums in our pilot projects, in part to see if this method would see that kind of similarity or differences among similar institutions. And in both of these institutions, they did have fire control levels that were in the level 1 to 2 range, and both ended up having very high fire risks. At the same time, they both ended up having just medium pest risks, even though both institutions had basic IPM. But nobody was trapping insects, and nobody was doing major statistics on how many moths they identified each year in their collections. That was not happening. And yet, they weren't getting infestations, and they weren't getting a lot of damage. They did get occasional pests, but it was one thing and a little bit of damage. So the risks were medium ones. Here now, I want to show you, these are summary and average results from all our projects, and I haven't identified which are which because I just want you to see the overall patterns. The purple bars is the average magnitude of risk for those 5 institutions, and I've included the preliminary data for science and tech, even though we haven't absolutely completed that report. So this data is open to changing, but it gives you a sense anyways. So that's the average of each of the 5 underneath. And what I want you to look at is some of the patterns. Even though each institution is individual and ultimately you need to know the risks for that institution, we can start to see certain things happening here. These are organized, the highest average risk by agent. So I've averaged over agent. These are not specific risks. These are average over agent from the highest down to the lowest based on the average amongst all these institutions. So what do I want you to notice? Fire, up near the top. And that's what we've seen in general. People have fire systems to a certain extent, but the control levels in most of our clients were at most a 3. And it was gaps, often gaps not necessarily in fire systems, but in training or procedures. So they just weren't having that full suite of methods, of measures in place. There is one exception that you see here, and this is an institution that does have everything in place. So it's got the fire systems, suppression in all its buildings, it's got training for its staff, and it's got good fire prevention procedures in place. It also has its collection in more than one building, so it is absolutely almost impossible to take out the whole collection by a fire, because in fact, I could say impossible, that all of these buildings, because some are across town, that all would go into flames at the same time. Wow, that would be very interesting. So that also brings its risk down. So it's the one that we've seen to date that falls below a magnitude of risk of 10. And then look at pests down here at the bottom. Medium risks at most. Some of them are low risks. Oh, I didn't want to go there yet. So for the institutions we have looked at, and we have not yet looked at an institution with a collection, say like a natural history collection, that is highly sensitive to pests and highly attractive to pests. For the institutions we have looked at, this is not a big problem. And all of these institutions are doing basic IPM, but they're not doing fancy things. Here is incorrect relative humidity that we often worry about. Down at the bottom in terms of average, but it actually reflects 2 different sets of institutions. First, right underneath the yellow bar, so it's on average, it's just not quite a 10 on average. There's a gap. That's an institution we didn't even look at. We didn't even analyze the risk. It was an archive. We looked at the situation. It was in the prairies. It did not get humid, it was dry, which is great for archives, and we looked at all the stuff in boxes and said, there's no fluctuation that we have to worry about. Didn't even go on the list. Then there were two where it was basically either the stuff is not affected by relative humidity, so a lot of metal stuff, or it was material that had been in a house for so long that it was essentially proofed, and if there was damage, you would need a more extreme event than had happened over the last 100 years, basically, is what we were looking at. But there are a couple here that did score high, and these are for very particular reasons, and just to show you that it's very specific to an institution. One is a historic house museum with a brick exterior, and we were modeling the risk should we humidify the interior to get that correct museum environment. And they knew from past practice of trying this that this would result in spalling of the brick. And this was Glamore. You saw the pictures. The building is the bulk of their value. So this ranked as high if they were to do that. If they were to go ahead and try to protect the contents, they would put their building at risk. The other is an art gallery that had an HVAC designed in such a way that if the humidification system were to fail in winter, which is when it's likely to fail because it's under heavy load trying to humidify the space, there was no backup. And it was a system that was very highly likely to result in an extended downtime to get the parts to fix the system. So in that case, we would see a drop in relative humidity in winter that could put a collection of paintings, and so including some paint films that are very highly sensitive to very low relative humidity at risk, and that ended up scoring a 10, which is, again, where we start to say maybe something should be happening to bring the risk low, although it's certainly not an 11 or a 12, as Stefan was talking about earlier. Finally, just to gloss over, we already talked about incorrect temperature. This is at the top because of collections with substantial holdings of materials that are of low chemical stability or medium chemical stability. So it's the archive with lots of low-quality paper, stuff from the mid-19th century to the mid-20th century. It's going to decay relatively quickly, as well as magnetic media and acetate film and negatives, things that go relatively quickly when they're stored at room temperature. As well, it includes our neighbors next door, science and technology, because they have a big archive that you saw this morning. It's not their most valuable collection, but it's huge relative to their object collection, and it again has these kind of issues involved. But they also have a lot of plastics in their collection. Part of the reason that that bar is so high is they have a lot of unstable plastics in their collection that they're dealing with. And so there was a whole bunch of risks that add up to give that value there. Those are those ones there. If those kind of materials are not present, incorrect temperature is a medium risk if we even analyze it at all. Medium risk is when we look at stuff stored in an attic that gets hot every summer. So the more we analyze risks, the more we can start to see what kind of factors get associated with these different categories. And we can start to use these colors and factors to say, okay, these are risks we should focus on, or these factors are present, so these are probably risks we need to worry about. These factors are not present, so there's not a risk here. And we can start to even begin to make predictions based on general factors rather than a specific institution, but only for the case at this point anyways, and what I'm interested in particular is emergency risks, for the case of risks that if certain factors are present, there is a high probability of the bulk of the collection being affected, and that therefore you end up having a very high to extreme risk. So, oh, see, it's doing that thing again, it just wants to be finished. So in the case of flood, what factors can we say are very likely to have a big impact on your collection, a negative impact on your collection? Well, storage of the bulk of your collection below grade on a floodplain. You have a high risk. That's the way it is, because almost unless you have a few pieces of very, very high value that are the bulk of the value of your collection that are not in storage, a flood in your storage which is going to happen eventually. And by the way, I've done some calculations. That is a flood, at least, even if it's only every 1,000 years, it's still in that area. So we're not even just talking about the 100-year flood. We're talking about very rare floods. It's still going to end up in that area. The other thing to worry about is if you have storage below grade in a space that's near old water mains or old sewer pipes, etc., which are known to break and send lots of water through your walls if they're very close. So storage below grade, not a great idea. Doesn't mean it's absolutely bad. It can be managed, so you need to know the details. But if these conditions exist, you can bet you're going to have a flood, and it's going to score up in this high to extreme range. So just don't do it. So I'm just going to end with a few comments, and this already came up, about new buildings, because sometimes we think this is how we're going to solve all our problems. And to a certain extent, it can work. And it does work. And we can use, in our projects, we've just begun to use graphs to give our clients ammunition to support the idea of a new building. Here, these are results from our Saskatchewan Archives Board project. And the bars in black, that's their current risk. And the bars on top in gray, that would be the risk should they put their collection in a new, properly well-designed building. And you can see that, just look at the number over here. So the yellow here defines that threshold of a 10 risk, which is high or higher, versus ones that are lower. And look at the number that were above 10 that fall below 10 by putting them in a new building that's designed to certain criteria. And there's even a few that we said, if you design this right, this particular risk, it's a specific risk, would just disappear off the map entirely. You'd have to look at the specific risks to know why that occurs. Here is, we can add these all up and know the total risk. So there's the total risk at the top. Essentially taking all of these risks that are affected by facilities and adding them together. And you'll notice that it's really the big risks that control the level of that total risk. So you can add a whole bunch up, but because it's an order of magnitude scale, it's the big numbers, and if you only have one big number, see, it's not that much higher than that top big number that control the size of the total risk. So we're looking at this, and this is actually not a bad reduction because the risk is so high. This new building it's not highly, highly cost effective, but it's starting to become something to think about. And if you think that's a small reduction, well, I'm just going to translate this into the linear scale. There's a linear scale graph showing the true reduction. So this is what they have currently. If they put it in a new building, this is what they have left. And this also shows very nicely what Stefan was saying earlier, why we do order of magnitude log scale, because all the little risks just drop off the graph and you can't even see them. And those were all those other risks that we saw before. So this can be very useful to support trying to get funding for a new building. Risk assessment can also be used, and we heard some more earlier this day, to support during the design and construction of a new building to make sure that certain things get in the new building. It's one thing to get people to agree to build you a new building, but then it's got to be designed properly to give the results that shows. And this comes from a project that Zedvis did in Brazil for the new preservation center of the Rui Barbosa House Museum, and he showed, early this morning, he showed the plan for that museum. Where he worked with the team, he set certain recommendations and criteria at the beginning, and then they worked through the process to make sure to try to meet all those recommendations. And here is his graph to show the degree of compliance with those recommendations. And by working it this way and having those criteria up front, they were able to make sure that 61% of 61% were fully observed, and then 16% were mostly observed, and then there's a handful that didn't quite. You know what a new building is, you get cuts, and there's certain things you have to just let go of. But most of the stuff ended up being there, which is really, really great, and that's one way you can use risk in new buildings. But I want to end by reminding you that risk management is a cyclic process, which means you come back to it. It's ongoing. And though a new building may seem like the goal that you want to solve all your problems, construction is also a key source of risks to collections, especially if it involves renovation on site. And of course, all new buildings eventually become old. This is the Victoria Memorial Building, which is now the Canadian Museum of Nature here in town. at the beginning of 1899. It's under construction. Just recently, the whole building did a whole new retrofit. Give it another 100 years and they'll be fussing about that building again. And that's life. Thank you.